Continuing section 6.1 here, a system of equations that has at least one solution is consistent. A consistent system is either independent or dependent. A consistent system that is independent has exactly one solution. Those are the ones we found on the last few examples. Something like 2, -1, 5, 7. Okay, so if there's exactly one ordered pair, then it's independent. It's dependent if it has infinitely many solutions. That happens if we get something like y equals 2x minus 3 and the same equation. So let's say it was y equals 2x minus 3, or it might be in point slope form or standard form, but eventually would give us the same points. If every point is the same, we call it infinitely many solutions, and it's dependent. A system of inequations that has no solutions is inconsistent, and we get those with parallel lines. Parallel lines never cross. We call those inconsistent and no solution. So in example 3 here, what is the solution of each system? Our first step is to graph each line still. So I'm going to do this one first because it's in slope-intercept form. Slope 1/2, y-intercept 1. So at 1, I have my intercept. Remember, that's our y-intercept. And my slope is half, so I go up 1 over 2. Up 1 over 2. I'm going to draw in my line here. And I'm going to extend it all the way through my graph because I don't know where my other points are going to be. Now, 2x minus y equals 2 is close to being in standard form, so we can find our intercepts fairly quickly here. To find my y-intercept, I plug an x in for 0, and I get my y-intercept to be at 1. So I cross the y-axis at 1. My x-intercept, I plug a 0 in for y. Negative x equals 2. Remember, we take the sign in front of the number with it. Divide by -1 to get rid of the negative. And my x-intercept is at -2. Now, if I connect those 2 points, and extend it through, I have the same line as I did with my initial one, with my initial equation. Since every point on these lines are the same, we say this is infinitely many solutions, because any ordered pair that will work for one equation will work for the second equation. Okay, now for B, I start at 2 for my y-intercept, and I go with my slope of 2, up 2 over 1, up 2 over 1. And again, we're just graphing those the same way we did in chapter 5. And my second one here, I start at -1 on my y-axis for my intercept, and my slope is 2, up 2 over 1, up 2 over 1, up 2 over 1, and there we go. I connect my dots, and if I look here at my graph, I can tell that these are parallel lines. I also could have told that right away from my equations, because we know that parallel lines have the same slope. So when I have parallel lines, I have no solution. These two lines right here are never going to cross. Okay, never going to cross. They never meet, never cross. So we have no solutions. There's no set of ordered pairs that will work for both this equation and this equation. Now go ahead and pause and give these a try if you'd like. What is the solution of each system? We can tell just by looking at these that we have a slope of -1 and a slope of -1. So we know these lines are going to be parallel, which means we're going to have no solutions. Remember, we can also do this for no solution, a null set, empty set, no answers. We could also graph, though, if you're not sure. So I can go to -3. If you don't happen to recognize right away that those are parallel, that's fine. -3, our slope is -1. So we go down 1 over 1, down 1 over 1. Connect our dots there. And arrows to show that they extend. Our second one, we start at 5, down 1 over 1, down 1 over 1. Connect our dots here. And these are parallel. Really take a look at your lines and see, do they seem parallel or do they seem like they're going to meet eventually and I just didn't extend my lines long enough? If we look at these, it seems pretty parallel. If they're off a little bit, it's just based off how I drew my lines. So no solution there. We can see that from our graph as well. On B, I'm going to start at -3. I'm going to go up 3 over 1. Up 3 over 1. Up 3 over 1. Start at -3. For my intercept. And my slope is 3 over 1. Connect them to form your line. And draw it in. Arrows to show that it continues. Now our second one, okay, I'm going to use intercepts again. You can divide by 3. Actually, I'll do that. Divide by 3. Oops. To get y by itself, we only have one step there to get it in slope-intercept form. And remember, when I divide one piece, I divide every piece in my equation. Now, my y-intercept is at -3. My slope is 3 over 1. So up 3 over 1. Up 3 over 1. When I draw in my line here, once again, I'm going to get the same line. And when that happens, we have infinitely many solutions. This could be a solution. This could be a solution. This could be a solution. Right here could be a solution. Even though it's not an easy thing to pick out, it could still be a solution. So we're going to say infinitely many solutions. That doesn't mean all solutions. If we pick an ordered pair that's not on that line, it's still not a solution. But if we pick any ordered pair that works for this equation, it will also work in this equation. And we can see that if we compare our equations as well. So, here, this equation, and once we got our second equation in slope-intercept form, are the exact same equation. So we know it's infinitely many solutions there, even if we wouldn't have graphed it. Take note on page 366 just summarizes and puts all of that information together. So it gives us the graphs and descriptions for inconsistent, consistent, and independent systems there as well. Real quick recap here. Systems of linear equations can be used to model problems. Systems of equations can be solved in more than one way. We did graphing today, and throughout the week we are going to do a couple other ways of doing these. One method is to graph each equation and to find the intersection point if one exists. And that's all for section 6.1.